All right, we are going to continue on in chapter 6 in this video by moving into section 6.3 titled Orthogonal Projections. You may recall from the last video that we briefly at the very end of that video talked about projecting a vector y into an orthogonal projection that we called y hat and an orthogonal vector we called z. We're going to focus more on that orthogonal projection, the y hat part, a little bit more in this video. We're also going to kind of move into a little bit more about spanning multiple vectors in this video as well. So kind of a little bit of a recap plus a little bit extra from the last video. The formula that we developed for you in the last video actually has an official name, and it's called the orthogonal decomposition theorem that says let W be a subspace of the nth dimension. Then for each y that exists in the nth dimension, it can be written uniquely in the following form. So this formula should look familiar from the last video, where vector y will equal vector y hat plus a vector z. Recalling that y hat falls in that subspace W, because remember that this is going to be a scalar multiple of a vector that is in the subspace. And remember that Z is always going to be orthogonal to the subspace W. And then as we also talked about in the last video, that as we can see, if you have multiple vectors, all right, we can say that they will be a orthogonal basis of W, all right? So if we have an orthogonal basis, so if you recall, orthogonal basis comes from the idea of orthogonal set. So remember, each vector uniquely has an inner product of 0. And we also talked about that if that is true, then they have to form a basis, which means each of the vectors is going to be linearly independent of each other as well. So assuming you have a set of vectors that form this orthogonal basis, we can actually find an orthogonal projection with multiple vectors in a subspace versus just one. So we can define y hat as being the addition of multiple different orthogonal projections. So the one that looks the most familiar to you, or should from the last video, is this first one. All right, where y dot u1 over u1 dot u1 times u1. Now drop the subscripts of 1. That was our projection of y onto a vector u. Now, if we have multiple vectors in this subspace, we will just continue this trend and we will add every multiple of the orthogonal projection. So if there was a u2 vector, you would do plus y dot u2 over u2 dot u2 plus times u2 plus, move on to the next vector. You're having to project each of these vectors with y. Now, once you find y hat, which is your orthogonal projection that's based on the orthogonal basis, you can then find a vector z that's orthogonal to the entire subspace by, similar to the last video, just rewriting this first equation in that z, the vector z will always equal y minus the orthogonal projection y hat. All right. So a few little notes about this orthogonal projection, and some of these will be repeated from the last video, and then I'll say them a bunch today as well. So first off, when you find y hat, we call that orthogonal projection. But more generally, what we're going to say now is that y hat is the orthogonal projection of y onto a subspace W. So some of y'all who have been in, let's say, a calculus class. I know in the Cal 3 class at Mississippi State, we teach this. We talk about projections in this way. So we have a notation that we use in that class that says PROJ sub W of y. This is just a shorthand notation for people who like to do orthogonal projection. I'm not going to require that shorthand in this class because we don't do as much of this than, let's say, in a calculus class that you might do. But if you're one of those people who likes little shorthand stuff, by all means use it. Another thing to keep in mind is that when you find y hat, this is considered the closest point to y in a subspace W. We saw this in the last video when I showed y'all the diagram of y hat, and it always falls right below the vector y in the subspace W. So therefore, it minimizes the distance and thus becomes the closest point. And then finally, a last thing you might hear this called is that y hat is also called the best approximation to y by the elements of W. Once again, that's kind of piggybacking off part 2, because if y hat and y are the closest points to each other, then we can also use y hat as an approximation element. And we're going to see this a lot more in the 6.5 and 6.6 videos. I'm going to talk about how we can use projections to approximate things and how we go about that. So we'll do a little bit more with number 3 later in this chapter, but I wanted to go ahead and get out in front of it now for terminology standpoint. So let's look at our first example of this orthogonal projection when a subspace is defined by more than one vector in the span. So my first of 4 or 5 examples here is verify that U1 and U2, the set, is an orthogonal set, and then find the orthogonal projection of y onto the span of U1 and U2. So let's answer the first question. Verify that we even have an orthogonal set, because if we don't, we can't do the orthogonal decomposition theorem. So I'm going to find what is U1 dotted with U2. So from the last video, we can say that 2 times -2 is -4, plus 5 times 1 is 5, plus -1 times 1 is -1. And if you add all those together, you do get 0, and thus they are an orthogonal set. Since that is the case, we can now write our formula for y hat as the following. And once again, all I'm doing is I'm piggybacking off this definition, but I'm only going to go U1 through U2 because that's the number of vectors in my set. So this would be the vector y dotted with U1 over U1 dotted with itself times U1. And then we're going to add to this y dotted with U2 over U2 dotted with itself times U2. And you just continue that until you run out of the vectors in your set. We have 2 vectors, thus we have 2 terms. So you have a lot of inner products to compute here, so let's do that. Beginning with y dotted with U1, that would be 2 plus 10 minus 3 over U1 dotted with itself, which is 4 plus 25 plus 1 times the vector U1, right, plus, now I'm going to dot y in U2, which should give you -2 plus 2 plus 3 over U2 dotted with itself, which is 4 plus 1 plus 1 times the vector U2. And now you need to clean this up as far as you can, because you want to end up getting one vector as your orthogonal projection. So let's see, a little bit of math here. 2 plus 10 is 12. 12 minus 3 gives me a 9 on top. On the bottom, that gives me a 30 in this case. Make sure that's right. Yep. And then 9 divided by 30, those both share a 3 in common. So that would be 3/10 times 2, 5, -1. Plus, over here, the -2 and 2 just cancel to give you a 3 on top. And on the bottom, that gives you a 6. So 3 over 6 gives you a half that we're going to multiply by -2, 1, 1. All right, so let's distribute our terms through. So if I multiply 3/10 through, that's going to become 6. Well, we'll simplify this. That becomes 6/10, which is just 3/5. And you're going to get 15/10, which is 3/2, and then -3/10. Plus, if we multiply a half through, that'll be -1, 1/2, 1/2. So add these together, make sure you're doing your common denominators correctly. So I'm going to go through these kind of quickly. if you take 3/5, and you add a -1, so you're subtracting, you should get -2/5. If you take 3/2 plus another half, that's 4/2, which is 2. And finally, -3/10 plus a half, well, that would be -3/10 plus 5/10, which would be 2/10, and that simplifies into 1/5. And thus, you have just found your orthogonal projection of y onto the span of U1 and U2. All right, so now I'm not making you find it here, but remember, keep in mind, that is the way that we would find a vector on this vector y hat that we just found. This is the vector that is closest possible to y, but it exists in the subspace W. Okay? So let's do another one. Now you're going to notice that a lot of these problems in this section are going to be very similar problems and processes, but the wording of the questions are different, so that gets you used to what could be asked of you. All right? So example number 2 says, find the closest point to the vector y in the subspace W spanned by V1 and V2, then find the distance from vector y to this subspace W. All right, so in this case, we are going to we have to make sure that we can even do this, because we can't do closest point, because when it says closest point to y, it's asking for y hat. You can't do that unless all the vectors in your span are orthogonal to each other. So kind of over here to the right, I'm going to verify what the dot product of V1 and V2 is. So that would be -4 minus 2 plus 0 plus 6, which does come out to 0. So we are good to go. For my formula to find y hat, so we're going to project y onto the subspace spanned by V1 and V2. So that's going to be y dotted with V1 over V1 dotted with itself times V1 plus the second vector in your span. So y dotted with V2 over V2 dotted with V2 times V2. So computing all of your dot products or your inner products here, let's see, let's dot y in V1. That would be 3 plus 2 minus 1 plus 26 over V1 dotted with itself, which is 1 plus 4 plus 1 plus 4 times V1, plus I'm going to dot y in V2, which would be -12 minus 1 plus 0 plus 39 over V2 dotted with itself, which is 16 plus 1 plus 0 plus 9 times V2. All right, we got to simplify these scalars in the front. So let's see, 3 plus 2 is 5, 5 minus 1 is 4, 4 plus 26 is 30. On the bottom, those add to 10. Well, that's real nice. 30 divided by 10 is 3 that we're going to multiply by the V1 vector. Plus, let's see, that's -13. -13 and 39 is 26. On the bottom, that is also 26. That's even better. That divides just to 1. So you're just going to add that second vector of V2. I'm going to distribute the 3 through. So 3, -6, -3, 6. That we are then going to add the V2 vector to, because we didn't pick up a number in front of it. And that's going to give me a y hat vector of -1, -5, -3, 9. And so that answers my first question. This is the closest point to y in the subspace W spanned by V1 and V2. That's your orthogonal projection. Now, the second question that I'm going to do in purple here is asking you to find the distance from y to W. Well, as we learned in the last video, to find distance, you have to have two vectors. Obviously, they told us y, And in order to use a vector that's in W, you want to use a vector that's as close as possible, which we have now talked about, that's going to be y hat. So to compute my distance, that's going to be the square root. And remember, you're going to subtract the elements of y and the elements of y hat and square each one. So that's going to end up being 3 minus a negative 1 all squared plus negative 1 minus a negative 5 all squared plus 1 minus a negative 3 all squared plus 13 minus 9 squared. This comes out to be the square root, and let's see, I'm going to kind of do some of this stuff out loud. 3 minus a negative 1 is 4, and 4 squared is 16. Come on, pen. There we go. 16, sorry. Plus negative 1 minus a negative 5 is 4, and 4 squared is 16. 1 minus a negative 4, or sorry, 1 minus a negative 3 is 4, and 4 squared is 16. And 13 minus 9 is 4, and you see it, 4 squared is 16. That becomes the square root of 64 when you add all those together. So thus, the distance from y to this subspace is exactly 8 units long, whatever your vectors are measured in. And so that is another way that we can use orthogonal projections to answer a question for us. All right. So what about this one? Once again, just different wording this time. It says find the distance from y to the plane in the third dimension that is spanned by u1 and u2. Once again, the wording here, when it's talking about a plane, we've talked about since chapter 1 that the spanning of vectors creates a plane in whatever dimension you're working in. So when it says a plane in R cubed spanned by u1 and u2, this is once again going to be y hat for us because we're going to eventually find the distance from y to this plane. So let's find y hat. Before I can do that, I need to verify that I'm allowed to do this, which means I've got to have an orthogonal basis. So I'm going to dot u1 and u2. That would be 9 minus 10 plus 1, which is 0. So we're good to go. So I'm going to write the formula down again. Hopefully by this one, you're starting to get the hang of this. To incorporate both vectors in my span into my orthogonal projection, y hat is going to be y dotted with u1 over u1 dotted with u1 times u1 plus y dotted with u2 over u2 dotted with u2 times u2. So computing my inner products here, if I dot y in u1, that's going to be negative 15 plus 45 plus 5 divided by u1 dotted with itself is 9 plus 25 plus 1 times u1. Oops, sorry, I forgot the 3. Plus y dotted with u2 would be negative 15 minus 18 plus 5 over u2 dotted with itself, which is 9 plus 4 plus 1 times u2. So figuring out your scalars here, let's see, that's going to end up being 30. That's 35 on top. And on the bottom, that's going to be 30. So 35 and 30 both share a 5 in common. So that's going to end up being 7/6 times my first vector. All right, plus, oops, sorry. Let's see, that's negative 33 plus 5, which is negative 28. And on the bottom, that's going to end up being a 14. So negative 28 divided by 14 would make this actually get rid of my plus sign. Get my eraser out. This is no longer, that's a highlighter, sorry. Instead of a plus, this is now going to be a minus 2 times my vector negative 3, 2, 1. All right, so distributing my numbers through. Let's see, 7/6 times negative 3, that's going to be negative 21 over 6 which reduces into -7/2. 7/6 times -5 doesn't simplify at all. That's -35/6. And then you get 7/6 on the bottom, minus, multiply this by 2, that's -6, 4, 2. Oh, and I just realized I made a mistake here. So this is a live action. I screwed up. I was wondering why the answer was so bad here. And I'm sure some of y'all were yelling at your video going, you screwed up, stop, stop, stop. I just realized that 9 plus 25 plus 1 is not 30. This should have been 35, which is way better because I was worried these numbers are about to get really bad. So that's a little better because 35 divided by 35 is going to actually make this a 1. So which actually makes this vector a little bit nicer. So I do apologize for that. I was very glad I caught it before I ended this recording here, or actually better that I finished this problem. So once again, let me repeat that. Once again, if you were yelling at the video, my bad. All right. I added U1 up wrong, dotted with itself. It should have been 35 over 35, which is 1. That's a lot nicer. And now I've picked back up here. We're still going to subtract these vectors. -3 minus -6 is +3. -5 minus 4 is -9. And then 1 minus 2 is -1. And so this is your orthogonal projection in the plane in this case. So now to calculate the distance, just like the last problem, we need to find the distance between the original vector y and this y hat that we just found. So this will be the square root. So we're using this vector in this vector as far as subtraction goes. That will be 5 minus 3 squared plus -9 minus a -9 squared plus 5 minus a -1 squared. So that's going to come out to be the square root of 5 minus 3 is 2, so 2 squared is 4. That's really nice. -9 minus a -9 is 0, so that just goes away. And then 5 minus a -1 is 6. 6 squared is 36. Right? That becomes root 40, which I know that root 40 is the same thing as the square root of 4 times 10, which becomes 2 square roots of 10 simplified. Once again, I probably am not going to care. If you want to stop at root 40, that's fine. Just know that on your homework, they may require you to break your radicals down. So make sure you're comfortable doing that as well. And so good job. Another distance problem. And that's kind of why we have this section. While finding orthogonal projections is great, all right, you use it to help you find a vector in a subspace that helps you then to find distance between two vectors. Now, once again, and I'm going to harp on this again at the very end of the video after the next problem, but this formula only works if you have an orthogonal set. If they don't form an orthogonal set, you cannot do this formula. All right. So to wrap up this video, let's look at a little more of a critical thinking question. So example number 4. Let these 4 vectors, so vectors u1 through u4, be an orthogonal basis for the 4th dimension. So I'm saving you a little bit of time here. I have given you 4 vectors, and you can verify if you would like. Every single unique inner product comes out to be 0. So they are an orthogonal basis. I'm also going to give you another vector v that's not in this basis. Let's let vector v be 4, 5, -3, 3. What I would like you to do is I want you to use the knowledge you've learned in the last couple of videos to help to write v as the sum of 2 vectors. One of them needs to be in the span of u1 and u2, and one of them needs to be in the span of u3 and u4. Now, here's the good thing. Here's kind of the idea I'm thinking behind this. If v, and just to make this easy, I'm going to call this number 1, and I'm going to call this number 2, just for numbering purposes. I want to write vector v as whatever I get for number 1 plus whatever I get for number 2. The good news is that you don't have to find both of these by doing formulas. Once you find one or the other, since you already know what V is, you could plug in what you found, you could plug in the V that you're given, and you could do basic subtraction to find the other vector you didn't do. So it doesn't matter which span you find. Whichever one you find, use it to help you find the other one. Just to be different, because we've always done U1 and U2, I'm going to actually do the second one, span of U3, U4, just so you can see that it does not matter. So for number 2, if I want to find V hat based on number 2's instructions, that means I'm going to take V dotted with U3 over U3 dotted with U3 times U3 plus V dotted with U4 over U4 dotted with itself times U4. So doing your inner products here, you should end up getting, let's see, V times U3. That's going to be 4 plus 5 plus 6 minus 3 over 1 plus 1 plus 4 plus 1 times U3. All right, plus V dotted with U4 should give you negative 4 plus 5 minus 3 minus 6 over the U4, which would be 1 plus 1 plus 1 plus 4 times U4. Now remember, I'm not checking if they were orthogonal because the problem already claimed that they form an orthogonal basis. So I know we're good to go. Working my way down, let's do our scalars. Let's see if I can not screw this up this time. 9 and 6 is 15, and 15 minus 3 is 12. 1 plus 1 plus 4 plus 3 is 7. That seems pretty bad. Let me double check myself. 9, 15, yeah, okay, so 12 sevenths. So this would be 12 sevenths times the vector 1, 1, negative 2, negative 1. All right, just double checking on my work. Whenever I get a bad answer, now I'm second guessing myself, but it all looks good. So then let's see. Negative 4 and 5 is 1. 1 minus 3 is negative 2. Negative 2 minus 6 is negative 8. And on the bottom, that's going to also be 7. So this becomes minus 8 sevenths times my next one, next vector. Distributing my numbers through. All right, that's going to be 12 sevenths, 12 sevenths. That's going to be negative 24 sevenths, and then negative 12 sevenths, minus, that's going to be negative 8 sevenths, 8 sevenths, 8 sevenths, negative 16 sevenths. Subtracting these two vectors will give me the following. That's going to give me 12 sevenths minus a negative 8 will be plus 8, so that is 20 sevenths. 12 minus 8 would give me 4 sevenths. Negative 24 minus 8 is negative 32 sevenths. And then negative 12, that'd be plus 16 would be 4 sevenths. So this vector answers the number 2 part. I'm going to go ahead and add an extra slide in so I have a little more room to do this. All right. So now moving down, I need to now find my vector 1 because I know what vector 2 is. I got this, and I know what vector v is. So rearranging that formula, we could simply say that vector 1 has to equal vector v minus what you found for vector 2 in this case. So let's solve for vector 1 that way. Vector 1 will equal the original vector v, which is 4, 5, negative 3, 3. I got that right? Yep. And then we are going to subtract from this the vector 2 we just found, while it is ugly, which is 20 sevenths, 4 sevenths, negative 32 sevenths, and 4 sevenths. So doing some arithmetic here, and you can double check me with your calculator if you need to. Let's see, 4 minus 20 sevenths is going to be 8 sevenths. Right? 5 minus 4 sevenths would be 31 sevenths. And then let's see, that's going to be negative 21 plus 32. So that should be 11/7. All right. And finally, 3 minus 4/7 would be 17/7. I'm gonna double check myself because I was doing this in my head. I have my calculator out over here, so let me double check some of these real quick. Just pause. You can pause the video at this point or check them yourselves. Okay. 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 Okay, all looks good. So that's my vector 1. And so now that I go back to the original problem, it says write V as the sum of 2 vectors. So for your homework, what they want you to do is I can now say that my vector V is going to equal the first vector, which we just found to be 8/7, 31/7, 11/7, and 17/7, plus the vector V2 that we found at the top of our screen here, which is 20/7, 4/7, negative 32/7, and 4/7. And if you add those together, this should come back out to be the original vector V. And so using orthogonal projection, we were able to break down a vector into 2 separate projections, possibly the sum of 2 projections in 2 different subspaces by using our ideas of orthogonal projection. So this ends my video on orthogonal projections, which is section 6.3 that we cover. In the next video, I'm going to move into section 6.4, which is titled the Gram-Schmidt process. The idea behind that is essentially, in a very quick form to end this video, what happens if the set of vectors that you're working with are not orthogonal, which means they don't form an orthogonal basis. It means you can't do orthogonal projection. The Gram-Schmidt process is a way to make any basis orthogonal, and thus you could do orthogonal projection.